Hello, everybody. And I wasn't here when we kicked off this morning, so can I just do a quick poll? Who here is working in astrophysics? No? Oh, one or two. Oh, a few. Okay. And who's working in physics or physics? Oh, the majority. Okay. What kind of physics? Fluid dynamics. Okay, that's the common theme. Fluid dynamics. Very good. Okay. All right. Well, I'll check with you as we go along to see that we're on the same page.
Some students are master students.
Yeah.
Who have not started their research, but they have some background in
Sure.
master thesis.
Sure. Okay. So, tomorrow Chris Jones is going to talk about magnetism that we know about on the other planets of the solar system, and my task is to talk about the Earth. And of course, the Earth is the object that we have the best information for, and indeed we've got quite a nice record from several hundred years of data that we can use to constrain the Earth. Now, it just occurred to me that there's a whole field of paleomagnetism, which in fact probably no one's going to talk about, but paleomagnetism is also very important for understanding the Earth. And any ideas what the oldest paleomagnetic record is on Earth? How far back in time can we go and actually make a measurement of the field at the time? How far back? Any ideas? Any thoughts? Fantastic. Thank you. Correct answer. So 3.5 billion years. So this is a considerable way back in Earth history, right? The Earth is about 4.5 billion years old. So that's an amazingly long way back in Earth history that we can go. So anyway, paleomagnetic data is very important. Paleomagnetic data tells us all about the reversals that have taken place in the Earth's magnetic field. But it just occurred to me that probably no one's going to talk about that at all in this meeting. Anyway, so we're going to really concentrate on the present, the recent past, and see what we can deduce about the Earth's field over the last few hundred years. So this is the basic plan of action, and we'll see how far we get. We might not get to the last topic, and if not, we'll come back to it later in the week. So I'm going to talk to you about some of the history, some of the measurements that are available for constraining the Earth's field, how we then treat those measurements, and we're going to look at the solutions to Laplace's equation, spherical harmonics, the international geomagnetic reference field, and then I'll talk in some detail about the inverse problem and how we use those measurements to infer something about the magnetic field at the surface of the core, which is much more instructive than looking at the Earth's surface. And we'll look at the models for the last 400 years. And then we'll start using some of the maths that Alex developed this morning. We're going to use some of the maths that Alex developed. Indeed, we're going to look at this limit where you put the diffusivity to 0, and then we can try and retrieve what the fluid flow is like in the core. And we'll talk a little bit about core mantle interactions. And then if there is time, we'll start to just discuss actual numerical models of the dynamo. So that's the plan. And I encourage you to just stop me and shout out at any point. I'd much rather have a little bit of dialogue than a monologue, because 3 hours is a long time. So I'll make all these slides available to you. We just agreed we'll put them on the website, so you can grab all this material. And there are some parts of this that I've put there for completeness, but I'll probably skip through quite quickly, but it's there for you to look at. So here's a selection of books, many of which maybe you know. We're actually in a nice time, because this thing called the Treatise of Geophysics came out already 10 years ago, and in fact it's being updated, so there'll be a revised edition coming out. But that's a very good starting place to learn about the core of the Earth and about geomagnetism. And then you have these, the famous book, you might call it the Bible of geomagnetism by Chapman and Bartels from about 70 years ago, and so on. So anyway, those are some sources that you may wish to refer to. So let's start by talking about the magnetic field, and indeed, how do we represent a magnetic field? So these are the conventional measurements that we might make. Anybody in the room made a magnetic measurement? A what, sorry?
Using Gaussian probe.
A what probe?
Gaussian probe.
Gauss probe. Oh, yeah, okay. Okay, Gauss probe in the lab. Yeah, okay. Yeah, okay, okay. But probably some of you have used the compass as well, no? Yeah, okay. Hope so. I mean, I know in this world of Saturn navigation that...
it's called the compass app.
Okay, yeah, I know. We're going to get to that. Yeah. So the magnetic field is, of course, a vector quantity, and so we can describe it by 3 Cartesian components, x, y, and z, or we can use 2 angles to say the direction in which it's pointing. So declination is the direction of the magnetic field in the horizontal with respect to the geographical north, and inclination is just the dip, the angle beneath the horizon that the vector makes. And then the thing that we'll call F is the intensity of the magnetic field, so the amplitude of that vector. So that's really all we need. Now, let's just talk a little bit about history. So I think this is going to be a counterpoint to all the algebra this morning. This is going to be fairly qualitative. So let's go back to the farthest back that we know of, and of course it was the Chinese who sensed the magnetism on Earth, and they developed these devices with a magnetized spoon, and the spoon could spin on its plate and essentially give you the direction of magnetic north. So this is going back essentially 1,000 years, and it wasn't till the 1180s that essentially the discoveries of the Chinese made it to Europe and were mentioned in some writings. Okay, so I won't go through this in any detail. So we know about declination, and then it wasn't till Robert Norman discovered inclination that we realized that actually the magnetic field was not in the horizontal plane at the Earth's surface. Now, let's get to around about 1600, and there are two very important measurements made that spanned 1600. One was the first measurement of declination in London of 11 degrees north, and then in 1634 another measurement in London of 4 degrees east. And this is, it just occurred to me, this is kind of critical because this was the first time really that it was recognized that the Earth was, shall we say, a dynamical system, or certainly that the interior of the Earth was a dynamical system. There was a demonstrable change in a quantity with time that made people realize that actually there was something going on which was changing the magnetic field. The thing was that you always had to worry about observational error, but these changes that took place over these 50 years, 11 degrees to 4 degrees, were too large to be attributable to observational error. So it was concluded here in 1634 that the field changes with time, and that's the phenomenon that we call secular variation now. And in the middle of that was the great work of William Gilbert. Remember, this is 98 years ahead of Newton. So Newton's publication, who's going to help me out? I'm suffering jet lag now. What is it called? Principia, thank you. Newton's Principia came out almost 100 years after Gilbert's De Magnete. So in a way, magnetism is essentially the oldest of the sciences. So here's Gilbert. Gilbert was the physician, so he's a medical doctor to Queen Elizabeth, and this was his publication where he did a number of experiments on things he called terrella. They were magnetized lodestones that he shaped into spheres, and he was measuring the magnetic field using little needles, and essentially concluding that the magnetic field from one of these magnetized objects was the same as was seen on Earth. Maybe we skip that. So here is one of the time series that will convince you, I think, that the magnetic field is changing in time. So here are some observations made from Paris over time, going back to the earliest observations. Maybe I put this in for Emmanuel. So we're going back here to maybe something like 1590, both with declinations and inclinations in Paris. And you can see that there is a considerable change with time, something like 35 degrees until 1800, and then the declination started going back towards zero.
So the present 10-degree declination is only recent, the one we have right now 10-degree declination changes 10 degrees, no? From north to the magnetic north.
Well, it depends where you are on the Earth's surface. Is it 10 degrees here? I don't know. We'll have a look in a moment. But, I mean, it depends where you are on the Earth's surface, the 10 degrees. We've got some maps coming up, so... yeah, everything changes. Okay, so so far we've got two of the measurements that we need to characterize the magnetic field as a vector. And it wasn't until 1832 that Gauss produced a method for measuring absolute magnetic intensity. So that was another critical step. So now we've got both declination, one of the pointing angles, we've got the inclination from Robert Norman, and then we're able to now characterize the intensity of the field, the length of the vector. So we're now able to describe the magnetic field as a vector quantity, and this is now only a little over 150 years ago. So that's essentially the development, 1,000 years of development in magnetism in 5 minutes. And it leads us on to the present era, which is an era where we're able to make global measurements of the magnetic field using satellites. And I'll show you what those are. So here's something that's of importance, is the continuous monitoring of the magnetic field using observatories all around the world. Here we are. India is quite rich in observations. There's a new observatory just down here on the equator in the Maldives that's been operating for the last 3 years with the assistance of some Indian colleagues. And we don't have some of the French observatories. There's Easter Island is probably here. I don't think that's Easter Island. Easter Island is here. Okay, so those are the observatories that go back all the way back to Gauss and the formation of the Göttingen magnetic union. So about 150 years of monitoring of the magnetic field. And you can see that through time, there's been a gradual increase in the number of observations. So this is the number of observations. 500 means, so you can make 3 component observations at an observatory, and that's how I'm counting them. There's something like 160, 170 observatories, each making 3 component observations. So that's why that looks like that. Okay, so I said that the state of the art now is to make measurements using satellites, and it's actually amazing to be able to make accurate measurements from space, and it's very technologically challenging, because you must orient yourself in the satellite extremely accurately So you need to know your you need to know the direction that the instrument is pointing to a few seconds of arc, right? So a few times 1/3600th of a degree. But this is achieved very well using star cameras that look out into the night sky and see the stars, and therefore you're able to actually achieve this kind of precision with the star camera that is mounted together with the the magnetic instrument. So you're actually able to make, well, we haven't talked about units yet, but you're able to make measurements of a few nanoteslas accuracy by satellite. Now, so the first satellites that we had oh, we've missed one. Okay, I haven't got a shot of it. But starting in about 1980 with MagSat, MagSat was very influential in providing 3-component measurements. The first time we had 3-component satellite measurements. And then about 15 years ago, we started this new era of satellite magnetometry with these satellites. One was called Ørsted. Ørsted is still actually in orbit. It's still kind of operating in a slightly crippled state, but it still sends some total field data down to Earth. So Ørsted is still operating after 16 years. The CHAMP mission started in 2000 and it ended about 2 years ago. So CHAMP is no longer in operation, neither is SAC-C. But the very important mission that is in operation is the one called SWARM. And SWARM was launched in 2013, October 2013, November 2013. And SWARM is very unique in being a constellation of satellites. So it's 3 identical satellites orbiting the Earth. They're all equipped with the same kind of instrumentation, the same star cameras. So here we have the star cameras looking out into the night sky, 3 of them. They're all mounted on the same optical bench here that also contains a 3-component flux gate magnetometer. And then at the end of the boom here, so this boom is about 3 meters in length, more than 3 meters in length. At the end of the boom here is a total field magnetometer, and intercalibration takes place between this instrument and the 3-component vector flux gate instrument that is here affixed to the star cameras. So the basic concern is that the flux gate may not, or is not really supposed to be an absolute instrument. It's really supposed to be a relative instrument, and you should, whereas you can make a proton magnetometer, which is an absolute instrument and can measure the field intensity, not the components, but it can measure the intensity of the field accurately of the order of 1 nanotesla, sub 1 nanotesla. So you use this instrument to calibrate the vector instruments. So that's the state of the art, and as you can imagine, when you have satellites in orbit, you have beautiful global coverage. There's a trade-off. I mean, it's very important to have the observatories sitting on the Earth's surface because you have continuous time series, whereas when you go into satellite orbit, you of course ultimately collect global coverage, but there is a sort of time-space aliasing that can lead to problems. So in many ways, many people feel that it's important to have both types of technology. Any questions so far?
Sir,
Yeah.
I don't understand the 3-component question. I think basically we require 1 component in the horizontal and 1 for the inclination. So how are the 3 components coming?
So I started by saying that, let's go back to the early times. You could measure declination, which gives you one of the angles, and then you can also use the same needle if you allow it to move out of the horizontal plane. It can also give you the inclination. And then you need to determine the absolute strength of the field. I didn't tell you how Gauss did this. Gauss actually invented a very clever way to discover the absolute intensity of the field. It's not a measure, not a way that's used nowadays, because we use either a proton or Overhauser magnetometers. So it's been superseded. So on this satellite, this is called an Overhauser magnetometer. Well, anyway, let's say it has a sub-nanotesla precision. Does that? Yep.
I have a question.
Yep.
So this curve is in the space. Okay, so it is possible that the solar wind's magnetic field can be also measured by this. So how can we distinguish between Earth's magnetic field and solar wind's magnetic field?
Okay, very good. That you're absolutely right. That measures everything. That measures everything. So it measures the external field, which is caused by the field in the magnetosphere. We'll come to how we deal with that in a moment. But yeah, that measures everything. So the key is to unscramble the different fields. So let's just say a few words about uniqueness, right? So let's pretend that there's no external magnetic field for the moment. So we've just got an internal magnetic field. What kind of measurements do you require to be able to determine that magnetic field, well, accurately and uniquely? Imagine that I give you perfect coverage of exact data. What kinds of data do you need to determine? So you can see that before 1832, before you have any intensities, it's clear you can't uniquely determine the field, because you can only determine the morphology of the field, and you could multiply that field by an arbitrary constant and scale it, and then of course you still have the same fit to the directional data, but you have a totally different field. So the field is clearly not unique unless you have intensities as well as intensities as well as directions. However, let's say, okay, we understand that there's clearly a scaling problem, but imagine, but other than that scaling problem, can you uniquely determine the magnetic field? And that's a tricky question, and it was proved about 20 years ago that perfect directional data on the sphere is sufficient to recover the, well, I've written the potential, but let's say the magnetic field uniquely up to this multiplicative constant, and the proviso is that the field is in a dipolar state. Now, maybe we're getting a little ahead of ourselves here, but the key thing is then that, so a dipolar field, of course, I think you all know what it looks like. The key thing is that a dipolar field just has two so-called dipoles, two places where the field is exactly perpendicular to the surface of the Earth. And so in that state, apparently, it is the case that you can uniquely determine the field. If you had a more complicated field, so let's say a quadrupolar field, something like that, in which you have 1, 2, and then maybe an entire equator where you have a dip. So these would all be dipoles. Apparently, it's then not that the problem is no longer soluble, and you cannot determine the field uniquely from just declinations and inclinations. Now, in the 1970s, so I alluded to the fact that it's very challenging on a satellite to collect vector data, because you need to be able to orient yourself extremely accurately. So you need to be able to look out into the night sky and determine which way your instrument is pointing. And so the idea was, well, why don't we just make measurements of the total intensity of the magnetic field, just the modulus of B. Maybe that's enough to characterize the magnetic field accurately. And indeed, it was possible already in 1970 to easily measure the magnitude of B using this device, which is the proton magnetometer. So you can see that to measure just the modulus of B, you don't actually need to know your orientation in space. Doesn't matter. Doesn't matter what orientation you have, you still measure the same B. So there was a thought, let's use satellites to just measure the modulus of B, and maybe we can accurately characterize the magnetic field. And unfortunately, so a very famous geophysicist called George Backus, he was working in San Diego, he showed by a direct counterexample that if you try to if you just measure the modulus of B, that is not sufficient to uniquely recover the magnetic field. There's an ambiguity. There's a whole family of magnetic fields. They're all different, but on the surface of the Earth, they would all have the same intensity, and away from the surface of the Earth, they're all completely different. So that's an unfortunate thing, but it is the case. And so just measuring B, the modulus of B is not enough. That's what really drove the idea that you must measure 3 components on a satellite. So quite an interesting proof. All right, so let us now return to some equations. Yeah?
So like the theorem which you just...
Yes.
The second paragraph, that says if the Earth is a perfect, if the Earth was a perfect sphere, only those two D and I would have been sufficient to characterize the whole magnetic field.
Yes, if you measure it on the surface of a sphere, just measuring the direction everywhere is sufficient if it's dipolar. So the key thing is you must only have 2 dipoles.
Okay, so like, let's just say, let's assume the Earth is spherical, and let's assume the magnetic field is dipolar. So
Yeah.
how bad that approximation is?
What was, say again?
How bad this approximation is?
Which is the approximation?
Like, the Earth is completely spherical.
Yeah, yeah.
And the magnetic field is completely dipolar.
Yes.
So like, how bad this approximation is when compared to...
Oh, sorry. Provided the field is in a dipolar state. What that statement means is that you only need you should only have 2 dipoles. That it doesn't mean that it's a perfect dipole. So it doesn't need to be a perfect axisymmetric state. Indeed, we probably at some point Chris might explain that in fact it's known by Cowling's theorem that you cannot have a self-generated dynamo that is a pure dipole, because it would have an axis of symmetry. So when I say a purely dipolar state, I really just mean this fact here that it just has 2 dipoles. It can be, so the Earth, we'll see in a moment, the Earth has 2 dipoles at the moment, and I'll show you the maps. It's far from dipole, it's far from symmetric or axisymmetric, you'll see, but it just has 2 dipoles. Thanks. Right, now apparently this is where we're going to differ from this morning. So these are my versions of Maxwell's equations. But anyway, we don't need too many of them, because I think I know where we're going with this. Let's just have a look here. So the the way that I would write this equation is. Well, maybe, did we have wedges this morning? Did we have crosses this morning?
That's the key.
These are my versions. I think we don't disagree on this one. Div B is 0. That's all okay. We don't really need that one, and we don't really need Faraday's law. So this is sort of Ampere's law in differential form. So the curl of B is mu naught times the current density J. So J is the current density, And probably this morning we didn't have mu naught. I'm not sure. Did we have mu naught? Mu naught is the permeability of free space, okay, which is 4 pi times 10 to the minus 7 henries per meter. Now, the only thing that we need to say is that if we make a magnetic measurement in this room here, or outside in the garden, or in space, the current density, we're essentially in an insulator here. Okay, it might not be true if we have a lightning strike. A lightning strike can come down, ionize the air, and somehow you would agree there's a current passing from above to below. But excepting lightning strikes, you know, we're essentially in an insulator. So J, the current density, is 0. So and we're working in a regime where this object, the displacement current, is 0. I think since many of you are doing physics, you know that this is only important for EM waves. So that would mean that if the current density is 0, then curl B is 0. And so if curl B is 0, then we could write down B as the gradient of a potential. And conventionally, it's written as minus the gradient of V. This sign is arbitrary, but the convention is to use the minus sign. And now, because of this other Maxwell equation, div B is 0, we find that this potential that I've introduced, it's an arbitrary potential, completely general. That means the potential must satisfy Laplace's equation, just like in the gravitational case. So that's the point of contact between magnetism and gravity. Now, I suspect we're not going to... Shall I whiz through this? I think, how many people know the solution to Laplace's equation in a spherical geometry? Just let's have a show of hands. Excellent. I thought probably everyone would. So we're going to assume that we know how to solve Laplace's equation, which is good. Perhaps I just stop and show you my notation. So I will write a spherical harmonic as PLM with argument cos theta, cos m phi, and the same with sin m phi. And these are the associated Legendre functions. And there are two quantum numbers here, L and M. Okay, so everybody happy with that? Yeah? So I'm choosing to write my spherical harmonics as real functions. Indeed, that's the convention going all the way back to Gauss. So that's good. We don't need any of this. So the general solution to Laplace's equation is of the following form. We have an internal and an external part to the solution. So here is the external part. So we're working in spherical coordinates, r, theta, phi. Theta is the co-latitude measured from the North Pole. Phi is the longitude measured from Greenwich by tradition, but it could be anywhere else. The French like to measure it from Paris, probably still. I can tell you a story. In 1884, there was a conference that agreed that longitude would finally be measured from Greenwich. But did the French do that? No, they continued for many years afterwards, and it caused me a whole lot of grief, I can tell you, because it's never documented. You discover it after the fact. Anyway, so here we have the part of the solution which is the external solution. So the key thing here is that we've got r raised to the power of L, and L is one of the quantum numbers, one of the spherical harmonic quantum numbers. So as r gets bigger, of course, that part of the solution gets bigger. So as we go out from the origin of the coordinates, that part of the solution gets bigger and bigger. Conversely, this bit here is multiplied by r to the power of minus l plus 1. So as we go, as r shrinks as we go towards the origin of the coordinates, this part gets bigger and bigger. Okay, so there are two contributions to this. This is a very general solution. It can represent all harmonic fields in free space, and it can represent sources which live interior to your observation point, and it can represent sources which live exterior to the observation point. So that's the general solution, but you all said you're you're experts on this. So now let's go back to Gauss. Gauss used his observations from magnetic observatories, which he set up. This is now around about 1832, 1835. So he took the observations, and one of the first questions to be answered. Oh yes, there's a question.
So the magnetic field, the theta is from the true north pole, the polar, the geophysical north pole, or the magnetic north pole?
So say again.
Theta.
Oh no, theta. Everything is in geographical coordinates. Yeah, the geographical pole defines. The north pole, and theta is measured. Yeah, today I will never use any kind of coordinates other than geographical coordinates. Yeah. Yep. Well, we haven't introduced any boundary conditions yet. Actually, this is just the general solution.
But actually, look, in the textbooks what we read, I'm not really into this. So they say that the true north, which is the geophysical north, is shifted by 10 degrees from the magnetic north.
Yes.
So the theta, if we are taking as the geophysical north, then we'll get very much off from the dipole.
Yeah. We'll come. Well, no. Maybe I'll answer that right now then. How can I? Let's just clarify this point. So you're getting ahead of me, actually, but anyway, that's okay. Yeah, we're definitely going to. So this is geographical north, and we're definitely going to measure theta from geographical north, and we're going to measure phi from Greenwich. Now, you know that the Earth's the Earth's dipole, for example, is kind of living somewhere over Canada at the moment. It's about 10 degrees away. You can represent that. You can represent that offset quite easily. So you're thinking that you could represent the Earth's field as a kind of dipole sitting at the center of the Earth, which you can do, but you could actually represent it as the contributions of 3 orthogonal dipoles, all of which add up, all of which superpose. And this one is clearly much stronger. In this is a virtual. This is not a real representation. This one is much stronger. But if you add together the effects of all these 3 dipoles, it would give you a. It can give you a tilted dipole. Basically, that's all that we need to say. So actually, the Earth's field. This is the 0th order approximation, right? This doesn't represent any physical reality, but the 0th order approximation is a tilted dipole, tilted by about 10 degrees, and therefore the magnetic field is something like that in the north. But we're going to see in a moment, when we see some real data, we're going to see that it's actually, even that's maybe not the best representation. Okay, more questions. So back to Gauss. What 150 years ago, people were wanting to know how much of the field is coming from in the interior of the Earth and how much of the field is coming from outside the Earth. And Gauss showed that if you took the three-component data that was, he sort of had, it was rather sparse, but he kind of interpolated it to a regular grid around the Earth and then analyzed it. He was able to show that you could do a formal separation of the internal part, which is represented by these, in my notation here, by these D coefficients, a formal separation of the internal part from the external part. And indeed, he discovered that around about, something like 99% is coming from the internal field, and that the external field is very small. So actually that now picks up on your, someone's question from here, I can't remember, which is that our satellite and our observatories, they measure everything, and the discrimination between the internal part and the external part has to be done mathematically. You can't do it any other way. You can't tell from the individual observation how much of it is coming from below and how much from above. But if you have a good coverage, you can actually do this formal separation between the internal and the external. So just a few other things he invented. He invented the method of least squares, Gaussian statistics. He threw that all into the hopper. It all came in very useful, and that was his conclusion. The geomagnetic field was mostly of internal origin.
So you're separating it like this. You're assuming that locally in that place there are no currents.
Yes, yeah, that's intrinsic to this whole separation. Yeah, we're solving Laplace's equation, so there's no currents. Yeah, yeah. Right, there's Gauss. He used to be on the German banknote, but it is no more. With the coming of the euro, there's no more Gauss on the German banknote. All right, now I'm going to I'm now going to just talk about the internal field entirely. So I'm actually going to change notation, and we're going to assume the field is entirely of internal origin, and we're going to write that equation for the potential V in this form, which is the very conventional form that you will almost always see. So these things here, the GLMs and the HLMs, which go together with the spherical harmonics, are called the geomagnetic or Gauss coefficients. And here, this factor A here is the radius of the Earth. So by convention, A is 6371.2 kilometers. It's the nominal spherical radius of the Earth. Of course, the Earth is an oblate spheroid, but that's a nominal spherical radius of the Earth. Yeah.
So this low current thing isn't justified on these surface because you use that approximation.
Sorry, what was the
low current?
No current, yeah.
On the surface of Earth, how is that justified? Because there is the interaction with the atmosphere and stuff that can create some sort of current density.
So you need to get up into the ionosphere before you start getting a sizable current density. And the ionosphere is, let's say 80 kilometers and above. So as long as you're operating below that, there's no problem. Now, a satellite, of course, is in low Earth orbit. A satellite is in orbit at around 500 kilometers, 400 or more kilometers. The satellite actually has a little bit of a problem. First of all, it can be flying through a region in which there are currents. But what's more, maybe we need a diagram for this, but what's more, so the ionosphere is here at, let's say, from 80 kilometers upwards, and the satellite is making its measurements, if you're on the Earth's surface on an observatory, the ionosphere is external to you, which is good because that means you can reject its signals very, very easily. But unfortunately, the ionosphere is now internal to you if you're in a satellite. And so if you have currents, so we have a J flowing through the ionosphere, the satellite sees that as actually an internal signal rather than the external signal that the observatory sees. Okay, but we won't go into it. I mean, the ionospheric currents tend to be diurnal. They're driven very much by the influence of the sun, cracking the molecules, creating conductivity, and the current systems essentially track the sun. So you get the most currents on the day side of the Earth, and they largely die out on the night side. So there is a way around this, but just to point out that life's not completely simple having the ionosphere internal to you on a satellite. It kind of helps, Chris, but it still doesn't. It doesn't entirely. You know, the ionosphere is internal to all of them. So it's in a way it's partly done by kind of temporal. By recognizing its diurnal signature really. And in fact, if you use the observatories together with the satellite, you've got more of a chance of. Okay, the final thing to say is that these things, the Gauss coefficients, so these are measured in nanoteslas. Now, I'm not sure what we were measuring in this morning, but anyway, that's the SI unit of the magnetic field is the Tesla, and the nanotesla is 10 to the minus 9 of a Tesla. So let me just tell you about this thing called the IGRF. So the IGRF stands for the International Geomagnetic Reference Field, and it is a model of the magnetic field that is produced every 5 years. And so you'll see that there was a magnetic reference field produced for 2015. So that's essentially for 1st of January 2015. It was produced around about just before Christmas last year. So that is the closest international geomagnetic reference field that you can find for the present day. Yeah, I know. Yeah, okay. Go on.
So we have 165 terrestrial observations.
We have what? Sorry.
160 or something. You said there are.
Yeah, 160 observatories.
How many satellites in the sky?
Three currently.
So the data is still not very dense, right? From your sparse data.
Unfortunately, I haven't prepared a slide, but the coverage that a satellite can produce. A satellite takes about 93 minutes to orbit the Earth. So you already get I can't remember how many it is. 18 passes, each on a different meridian, even within a day. So if you take a data set from a satellite mission from even 3 weeks, maybe after the break I'll show you. But it's impressive, right? You get very nice coverage. So very quickly you can get very good coverage. Yeah. Okay, I thought you were going to ask a different question because this one is now we're now equipped to answer or come back to your question about this business, because these three coefficients in the Gauss representation, each of them, so G10 represents a dipole which is aligned with the rotation axis. G11 represents a dipole which is coming out of the Greenwich meridian at the equator, and H11 represents a dipole which is coming out 90 degrees away from the Greenwich meridian. So you can see from the amplitudes of these, how much stronger the axial one is. But I mean, this is 5,000, that's 30,000. So there is, you know, there's a sizable equatorial dipole, and that's what contributes to offsetting the field. But I'll show you in a moment, because we've got some maps coming up.
What is this? SV?
Right, so that's a good question. So all of these show you the Gauss coefficients for a particular snapshot, a particular epoch, and then this is the rate of change of the magnetic field for the next 5 years. So this tells you that that at present the Earth's dipole is increasing by 10 nanoteslas per year, and you'll see that over a period of 5 years it will it changes by of the order of 50 nanoteslas. You can see that. So this is the predictive element. If you use that last determination together with the secular variation, it allows you to make a prediction at any point on the Earth's surface at any time during this period. So you just need to add that on to the So after the break, we'll be doing a test on some of these numbers. So please remember them all. They're all critical. There's another page of them here which you might want to remember. Okay. So let's actually get to some. The highest what? Oh, just up to degree 4. Yeah. I just put them there so you could get the. I mean, so they go up to degree 13. So okay, so you have some knowledge of spherical harmonics. How can you imagine how many coefficients are there in total if you go up to degree 13? Can you remember? I mean, within a specific L, how many M's are there? 2L plus 1, right? Okay, so you've now got to just, for each L, you've got to add together 2L plus 1. You can see it's a triangular sum. How many does it give you in total? It's okay. I'm just throwing that in for fun. But so you have L into L plus 2 coefficients. So if L is 13 is the truncation point for the IGRF, then you would have 13 times 15 coefficients, which I don't know what I think it's 169, is it? Well, I think it's definitely an odd number, I think. I think it's 195, thank you. Okay. I was just following the adage, never do mental arithmetic, you know, at the blackboard. It's never going to work, yeah. So that's the number of coefficients then that are used to describe the field. Well, not under my, okay, I understand, but not under my, you see, under the way I've written it, you see, I put the causes and the sines separately. I'm using real spherical harmonics. If I used, yeah, I could use complex spherical harmonics, I could have the m's negative, but then I would have a condition that comes about because the field is real that I'm describing. So that's the convention. It goes all the way back to Gauss. If you have any problems, just talk to Gauss. Okay, so let's have a look now at some of the maps of the magnetic field. And this is the declination. Okay, this is already for 15 years ago. This is 2000. But you can see, so here's one of the dipoles down here at around about minus 65. It's between New Zealand and Antarctica. And the other one is actually off the map. It's up here, sort of in, well, northern Canada. But the key thing you'll see is that this is really quite a complex field. Okay, it's not so simple. So it shows you that the idea that the magnetic field is a dipole is a little bit misguided, right? It's too simple. And that just reminds me that. So these are in degrees. These are it's the declination in degrees. So it's the angle that your compass would deviate at any point from the Earth's surface. So obviously the declination is not very large here in India. Incidentally, it's not very large in Switzerland either. So we actually share the same if you went to Delhi and Switzerland are sharing the same contour.
What I'm asking is, if it were a dipole, what should you see?
Oh, if it were a dipole, well, where would you like the dipole to be aligned with the rotation axis? In that case, you would see 0 everywhere. The map would be devoid of any contours. It would be 0 everywhere. Yep, that's what we would see. So, I mean, look, the fact that you have declinations which are, large as, well, once you get near the poles, they can be arbitrarily large. But, typically, 25 degrees in South Africa, it's quite sizable, the declination. I just realized that I forgot to show you one of my first movies. So let's just have a quick look at that. So I've just shown you what the declination looks like at the present day, but we're going to talk in some detail about how these models were created. But let's go back to the year 1610, and this is what the declination looked like in 1610. So orange is westerly declination, blue is easterly declination. And this is the line of 0 declination. And in 1610, it passes, well, in about 1590, it passed through this point here. This point here was called, I'll write it on the board. Oh, it still is called Cape Agulhas. So in Portuguese, Agulhas means needle. So it's Needle Cape. It's the Cape of the Needle. And it was named because it was the place where the declination was 0, and people thought this was significant. Now, remember, 1610, we haven't yet discovered secular variation. People thought, that's great, it's 0 there, we'll name it at 0, we'll name it Cape Agulhas, and it'll always be like that. But the problem is that as time went on, I'll just play this forward, you see, unfortunately, the 0 of declination is swept all the way across the Atlantic, and this point of 0 declination now has about 25 degrees of declination, so that brings us almost to the present day. Oops, I've forgotten how to do this. There we go. Okay, so then the inclination is a little bit less exciting, but nevertheless, there's still big deviations. If this were a pure dipole, these lines would be entirely horizontal all across the map. Possibly the more intriguing one is the intensity of the magnetic field. So these are the contours of the intensity, and obviously it's the most intense near the poles, but in fact you have 2 foci in the northern hemisphere where the field is up to 60,000 nanoteslas in intensity. But look here in the South Atlantic, right? The field is incredibly weak here. So you've got a low which is less than 25,000 nanoteslas compared to the 60,000 nanoteslas near the poles. And it's low even compared to the value in India, which is around about 40,000 nanoteslas. And that means it's time for us to make our measurement. We'll just check this. Okay, so who has the app called Magneto? Yeah, you see, there must be a lot of... We don't know what this building is made out of, but anyway, this claims it's around about 30,000 nanoteslas in this room, which doesn't seem to agree very well with the IGRF, which says it's about 40,000. So, okay, I'm already up to 55,000. So it really depends. It really depends where you. Okay, that's about 40,000. Now do you believe me? Okay. So as Alex said, it's all done with apps now. So.
But this is the other is supposed to have magnetic.
Say what? Yeah, it has a magnet. It has 3-component Hall sensors. Yeah. Yeah, those were actual measurements.
It wasn't checking from the internet.
No, that's measuring the field in this room. Okay, right. So we're getting through. Now, let me just finish. Well, we're going to get to this in a moment. So, yeah, it's a very good question. I'm going to show you the consequences of the field being weak there. So this thing has become called the South Atlantic anomaly, and it has consequences particularly for satellites because the shielding effect of the magnetic field is weakened there. So many of you know that the magnetic field shields incoming radiation, it deflects the charged particles, and I'll show you the evidence that this has got some bad consequences for satellites. So this is a satellite called TOPEX. It was flying at 1,000 kilometers above the Earth's surface. And these are, all these yellow dots are anywhere in its orbits where it has problems with its memory, or essentially memory losses. And then this was actually the place where it ceased to function. So, and these are the contours of the South Atlantic anomaly. So you see the way that they are arranged very much in agreement with these contours. I have another example. This is UOSat. UOSat's flying at 700 kilometers. That shows very nicely where you get all the problems in the South Atlantic anomaly. And you can actually make the measurement of the flux of charged particles. So this is electrons and protons measured by SAMPEX at an altitude of about 600 kilometers. And you can see how many more of these energetic particles make it to an altitude of 600 kilometers because the field is so much weaker there. So that's electrons and protons, and this is another graph showing trapped electrons with energy greater than 300 keV. So you can see how important this is, and it is a concern for satellite technology. I mean, if your satellite's going to fail, it's most likely going to fail there. Okay, so I think that takes us to the end of the first little bit. So, any questions? Yeah.
Do you have a similar video for this intensity also?
No, I didn't. I haven't made one. But you see, actually, there's a problem there because I can only go back strictly to 1832 with intensity, because that's as far back as I know the intensity of the field. Whereas the declination I know from a long time ago. So, but it's definitely of interest. So let's just say that this seems to be weakening. The field seems to be weakening gradually with time. I think that's the the sort of the direction of your question, that we see it's actually getting lower and lower and lower with time. Yeah, yeah.
So, in other words, it's like the morphology is typically frozen in this structure?
Not really frozen, no. It's the morphology has changed, but it has been weak there for the last 100 years, shall we say, but it seems to be weakening more and more there. Yeah.
What is the current prediction according to secular variation, whether it would be sustained for how many years on the observed data?
Sustained.
It's like this morphology of the total intensity. How much it would be? How many years it would be sustaining in this structure?
Well, the thing you'll see, maybe I can answer that a little later. The thing you'll see is that the field is actually evolving quite slowly. Let's say it's going to be sustained for of the order of 1,000 years. The field is actually changing fairly slowly, but there is, a small gradual percentage decrease all the time in that South Atlantic anomaly. So, I mean, I think something like 1,000 years is my answer to the kind of time scale you're talking about.
So is that fast compared to the secular variation of the declination which we observed? It seems like the declination is moving, is changing very fast compared to the contours of the total intensity. So why
Well, I haven't shown you. Okay, I haven't shown you. I can't really answer. I haven't got a video to show you, but they're both evolving on a similar kind of time scale, to be honest. I mean, the declination looks faster because it's sort of rotating around the Earth. It's slightly advecting. It's sort of advecting this South Atlantic anomaly with it, right? You can actually see that very clearly. So it used to be further into the Atlantic, and it's gradually moving over Brazil. So Brazil is suffering the effects the most at the moment. But the pattern sort of moves along with the declination, shall we say? Yeah.
So in the picture for the intensity, you showed two strong patches.
Yeah.
Where does it show up in the globe?
Yeah, well, you see, this is why we must abandon, maybe I should have made an announcement here, we must abandon this idea that the field is a dipole, right? And indeed, you've just pointed out very clearly that the field, depending on which component you look, the field is not a dipole. Indeed, you get two very strong patches. If you bear with me a moment, we're going to start, the next thing we're going to do is to look at what the field looks like at the core surface, and we'll see exactly how non-dipolar it looks at the core surface. And once you've seen that, you might think it's amazing that the dipole is a reasonable approximation. But yeah, absolutely, you get these two strong features over Siberia and Canada in the intensity. So yeah.
I was reading somewhere that this decreasing in intensity is an indication of the magnetic start of magnetic reversal, kind of.
You do indeed read that.
Okay.
So yeah, I mean, the thing is that it's a really difficult one. Yeah, I said that we weren't going to discuss paleomagnetism, but paleomagnetism is important in this context. So the last geomagnetic reversal was about 780,000 years ago. That's the last full polarity reversal that was sustained. And if you look over the last 5 million years, you will find that the field has been reversing on average something like twice per million years, roughly. So in a way, first of all, we're a little bit overdue statistically, but that's just statistically, We're a little bit overdue because it was a long time ago, the last reversal. But of course, it's very difficult to actually know what a precursor to a reversal looks like. A reversal itself takes something something on average of about 5,000 years to be accomplished. There's a little bit of plus or minus on that, depending where you are on the Earth's surface. But we know from the paleomagnetic records that it's something like 5,000 years. So on human timescales, it's very difficult to discern what a reversal looks like. But I cannot say that it'd be interesting to know whether this is the start of a reversal and that in 5,000 years' time, maybe we have had a polarity reversal. That might be the case. It's just very difficult to say what is happening. But yeah.
So there's another related question. So this field work, I'm sorry, what is it called? It's field measurement inside the ocean.
Paleomagnetic measurement.
So can one say that quadrupole, can you get higher moments from that data? Quadrupole or octopole?
It's very difficult. It's not. I mean, people try. It's very difficult for reversals. I mean, if we look at the average field in the past, people try to tease out the quadrupole from the dipole. During reversals, it's very, very, very difficult because you've actually got to get contemporaneous measurements of that reversal from different sites all around the world. And measurements of reversals are not so numerous. But there has been work on this, yes. But it's very difficult to say exactly what happens. So. I mean, one thing you can rule out, I mean, probably the field is not dipolar all the way through a reversal. I mean, certainly it becomes dominated by multipolar components. I think that's fairly clear. Well, during a reversal, the intensity drops to about 20% of the pre-reversal value and then rebuilds back to its sort of pre-reversal value.